All current forms of rockets use Newton's third law of conservation of momentum, which is every action has an equal and opposite reaction. This is where all momentum prior to an event, normally a collision, is equal to the momentum immediately after the event. In rocketry terms, that means that if you have zero momentum before you start your engine, you still need to have zero momentum after you start burning fuel. Let's say we have a rocket on a launch pad. This means that when you launch the rockets exert a negative momentum on themselves because of the momentum of the burning fuel being released downwards. However, since the momentum has to equal zero overall, then that means you need some positive momentum as well. This positive momentum is used to move the rockets upwards while the fuel is moving downwards. However, the rockets will move upwards at a fraction of the speed of the fuel being released downwards, as the rocket has a much higher mass than the fuel does. For example, let's say we have a water bottle rocket. Immediately after the launch, your rocket may release 100 grams of fuel at 3 meters per second. But then the rocket with the remaining water inside, let's say it weighs 500 grams, will only move at 0.6 meters per second. The fuel that is being projected, in this case water, is called the working mass or the reaction mass. In a real rocket, combustion is used to increase the temperature of the gas in the rocket and expand the gas inside, increasing the pressure. This rushes through a nozzle and thus the rocket moves from the idea of conservation of momentum. In a rocket, you need an oxidizer in order to perform combustion, since there's no oxygen in space. But other than that, the idea of rockets are exactly the same as a standard jet plane's engine. A rocket's propulsion is measured in terms of delta V, which is proportional to the thrust per unit of mass, and is often used to determine the mass of propellant needed to perform a maneuver using the Tsiolkovsky rocket equation. Most modern spacecraft started to be based upon standard terrestrial engineering, like that found when designing trains, cars, and planes. However, it developed gradually into a more advanced topic, since space is a much harsher environment when compared to Earth. Modern spacecraft are made of various subsections. These include the main structure, which holds everything together, a control and altitude determination module, which controls the orientation of the spacecraft. All of the complicated orbital calculations happen here. A communications and command module, which holds the electronics used for communication and allows the craft to communicate with ground stations and satellites. A power module that deals with collecting solar energy, storing it, distributing it through the spacecraft with wiring, and then a regulation system to stop it from overheating. A thermal unit, which maintains the temperature in the craft, and a propulsion module, which provides thrust to the craft if it needs to be shifted back into the correct orbit. Most modern spacecraft have their structure made from metal composites. This is where they combine a metal with the desired properties such as carbon fiber or aluminium, make it into a matrix by splitting it into layers or wires, and then join it together with epoxy resin. They are designed this way as it maximizes the strength of the structure while reducing the amount of metal used, that way letting it be much lighter. Currently, most spacecraft use radio signals to communicate with stations on Earth. However, some of the more recent spacecraft use laser communication systems. This requires line of sight with the receiver, but transfers data at a much faster rate than a traditional radio system could. It can work for both satellite to Earth and satellite to satellite communication. This works very similar to fiber optic cables. You simply turn a laser on and off to represent binary code. However, in space you need to use a highly focused laser and point it at a relatively large receiver panel, and then you rotate the laser to always focus on the receiver. Of course, this means you need to know the exact location of the receiver relative to you, but this can be easily calculated with modern computers. Most rockets used to exit our atmosphere are currently chemical fuel rockets. These were explained earlier. However, there are some other forms of propulsion that are used in other situations. Despite sounding like something from Star Trek, ion thrusters are regularly used today. These are a form of electrical propulsion where rather than using fuel to gain forward momentum, you instead use ions. Of course, because ions are so light, the thrust created by them is very small. However, they are very weight efficient compared to fuel rockets and so are often used to move small probes through space or to change the orientation of larger crafts. For instance, the Deep Space One rocket managed to get a delta V of 4.3 kilometers per second using only 74 kilos of fuel, which is very large. However, because the thrust is so small, they are useless when trying to escape gravity and so need to be used in orbit. They still have drawbacks. They only have a lifespan of about 3 years and their acceleration is slow. It took the Dawn craft 4 days to reach 60 miles per hour. It's easily seen that weight equals money when it comes to spacecraft. If you lower the weight, then that lowers the amount of fuel needed to cause a suitable amount of acceleration, and so that further lowers the weight. However, obviously you cannot replace a thick steel plate with aluminium foil, because it reduces the structure stability. So new spacecraft need to use lighter materials that have the same strength as the heavier ones. One possible solution is the use of carbon nanotubes. These are very strong for their weight, such that if you had the same mass of steel and carbon nanotubes, the nanotubes will be 600 times stronger. They also have an interesting property in which they have a hole in their middle. This is enough space for a few atoms of copper, and so you have microscopic wires within your structural support. These wires, made on the atomic scale, can be used to reduce the bulk of wiring used in today's power modules. This gives the possibility of being able to use structures as part of designs, rather than as a container for the important parts within. We are already beginning to use structure as a part of design with the idea of spacecraft skin. Let's think about our own skin briefly. It tells us when we touch something hot, sharp, or something that could otherwise damage our body. A spacecraft skin can do the same thing. It's a set of sensors only nanometers across in the form similar to that of a sticker. They can be made to detect if a part of the structure is about to fail and tell a central computer, just like our own skin tells our brain if something hurts. If we go back to the skin analogy, our skin also heals itself. There are currently some types of smart materials being experimented with that can do just that. These self-healing materials use small capsules of healing agents that cause polymerization in reaction to a penetrating object. There are currently several ideas on how to approach interstellar travel. These include small unmanned probes which travel at extremely fast speeds, close to the speed of light, a manned craft which will have the same speed of modern spacecraft. However, this will involve generations of people in the craft, due to the large distances involved. This will mean that the craft will likely need to be very large, possibly the size of a city. It also means that processes need to be developed for collecting water and maintaining a food supply. There is also the idea of fast manned spacecraft, in which you will be traveling at a relatively large fraction of the speed of light. This is faster, may not require generations of people, and also introduces the idea of time dilation. Time dilation is where the elapsed time between two events is different to two different people. There are multiple types of time dilation, but the one that applies the most to space travel is relative velocity time dilation. This is where the speed of two people varies greatly. The one traveling faster will experience time to be slower than the one who is traveling slower. In this animation, let's say that the blue clock represents a person on Earth. The red clock represents another person. The red clock's person is moving faster than the person on Earth, and so is experiencing time to be slower than the person on Earth. This isn't just psychologically, but also physically. This means that if you are traveling hundreds of thousands of times faster than those of us on Earth, you may return after 5 years of your time, but your friends from school may be living in care homes when you return. Time dilation can be a very good thing for astronauts. Let's say that an astronaut can only be active from 20 to 60 years old and can only have one generation of astronauts on the ship. In that case, it suggests that you can only go to 20 light years from Earth for a round trip, assuming you don't stop anywhere and you go at the speed of light. However, due to time dilation, you could do a 32 light year round trip without reaching light speed. This would happen if you were to accelerate at 1g for 1.32 years, coast for 17.3 years, and then decelerate by 1g for 1.32 years. You could have a quick stop off, and then go back. This would take 40 years of ship time, but you'd be back 76 years later in Earth time. Of course, if you were to accelerate at a higher rate, you could travel even further in the same 40 years.